Hello everybody, I hope you're all doing well. My name is Pedro Cândido and today we are here to continue our course on the acid-base disorders, okay guys? Well, first of all, don't forget to leave a like on the video, okay? Subscribe to the channel to help us to grow this immense community, okay? We all of our contents are free here on Mad Knowledge, okay? So, first of all, let's start, okay? Today we are going to talk about the metabolic acidosis, okay? We are going to go a little bit deep on this topic. So, starting, let me get the laser, okay? Uh, just to remember, okay, if you have a metabolic acidosis, we need to have a value of pH lower than 7.35. And we need to remember that because it's a metabolic acidosis, it's due to a low bicarb, okay? It's the kidneys cannot regulate this pH well, okay? So a few causes of metabolic acidosis is diabetic ketoacidosis, renal tubular acidosis, lactic acidosis, and some intoxications, okay? And we can classify this metabolic acidosis use the value of anion gap, the anion gap, sorry. And we are going to talk about anion gap just in a second. But first of all, we can have a normal anion gap, an increased anion gap, okay? And we can have a decreased anion gap or a negative anion gap, okay? So let's talk about the anion gap. I'm going to explain for you what's the concept behind this. Okay, I draw these two columns here. Okay, they both represent these ions in our blood. Okay, we have the cations. Okay, that the positive ions and the negative ions here in this side, the anions. Okay, and here you can see that sodium it's it's the largest number, okay, of cations on our blood. It's due to sodium. And in the other side, you can see that here we have chloride, we have the bicarb. Here in Ag, it's the anion gap. And okay, so you can see that these two columns are equal, okay? We need to have, how can I say, okay, we need to have an electric neutral environment, okay? So all of our positive charges needs to be equal to the negative charges. And here in UC, it's the unmeasured cations, and here in UA, it's the unmeasured anions, okay? What does it mean to it's a measured or unmeasured, okay? In order to calculate the anion gap on our day-to-day in the hospitals and clinics, we don't calculate all of these ions, okay? We don't ask exams to calculate them. We ask just sodium, chloride, and bicarb, okay? And if you can see, okay, the value of the anion gap, it's the UA minus the UC, okay? We will end up with this. But there's another way to calculate. If you see in the columns, okay, if we forget this upper part, okay, I'll just like draw them out here. Okay, we'll still end up with two columns that are the same, okay? And that you can see that an ion gap is still here. So if we take sodium and subtract the value of chloride and bicarb, we will still end up with the value of the anion gap, okay guys? So that's what we do, okay? The equation to calculate the anion gap, it's this one, okay? It's sodium minus chloride plus bicarb, it equals 12, okay? Usually less than 12, you can see reference that this value can range from, can range from 8, okay, to 12. So Pedro, what are the causes of a metabolic acidosis with an increased anion gap? Okay, you can see here I got a mnemonic for you to try to remember this more easily. So it's mud piles. It's so we can add like cat also, cat mud piles. So first of all, we have methanol poisoning, we have uremia, we have diabetic ketoacidosis, we have paraldehyde and fenformin intoxications also, isoniazid, lactic acidosis, ethylene glycol. Ethylene glycol, we have an example here in Brazil where there was a brewery that had some of the beers were there were ethylene glycol were leaked into the beer, and some people also actually died because of this. Okay, we'll talk about this later, where you can identify through some labs if the person is intoxicated with this kind of material. Okay, so we have the salicylates, and we also have the cat part here. Okay, we can have carbon monoxide, cyanide, and congenital heart failure. We have the aminoglycosides, the antibiotics, and the theophylline and toluene also intoxications. You can see that there's a lot of intoxications here. I don't know why my laser is lagging here. Okay, I'm sorry, but let's continue. We have some normal metabolic acidosis with a normal anion gap. Okay, like the renal tubular acidosis and the diarrhea. And we have some causes of negative anion gap that we'll leave for another class. Okay, so it's basically this that what I had to explain for you. And now we're going to practice with some questions, okay? So let's start here. To calculate the anion gap of a patient, the following parameters are required. Potassium. No, we saw that we don't actually need potassium. Bicarb. Okay, we need. Magnesium. No. Potassium also no. Calcium no. Phosphate. No. Sodium. Yes. Calcium, no. Phosphate, no. Sodium, yes. Calcium. Potassium, no. Chloride, yes. Sodium, bicarb, and chloride. Okay, guys, you saw up in here. That's all we need to calculate the anion gap. Okay, guys. Okay, let's go to the next question. It constitutes a cause of metabolic acidosis with a normal anion gap. Okay, lactic acidosis? No, we have just seen that this is a cause of an increased anion gap. Diabetic ketoacidosis also, uremia also, salicylate poisoning also. Okay, what we end up too with diarrhea. Okay, it's also here if you can see. Okay, anion anion gap, diarrhea. Okay, next question. In a patient with a pH of 7.12, okay, so it's an acidosis. We can see. Is it a metabolic acidosis? What do? We need to look at the bicarb number, okay? It's a lower bicarb, so of course it's a metabolic acidosis. Sodium of 100, 130, chloride of 90. The most likely values for PCO2 and anion gap are respectively. So we need to calculate the expected PCO2 for this situation, okay? If you remember the other class, we learned how to calculate that, okay? So the expected value for PCO2 will be 1.5 times bicarb plus 8, okay? Oops, this 8 was horrendous. So the PCO2, the expected PCO2 in this situation will be, so if our bicarb is 10, it will be 15 plus 8, it will be equal to 23. Oh, okay, we already have 23 here in the answers. We didn't even have to calculate the anion gap here in order to answer, but we'll calculate this anyway. So the anion gap will be equal to sodium 130 minus 90, that's the value of chloride, plus 10, that's the value of bicarb. So it will be 100 here. So we end up with an increased anion gap here of 30, guys, okay? So 23 and 30. Let's go to the next question. Consider the following data, okay? pH is 7.2. We can see that it's an acidosis, bicarb of 17, so it's a metabolic acidosis, okay? And PCO2 of 33. Anion gap, it's equal to 19, okay? It is compatible with metabolic acidosis with an increased anion gap. Okay, so now we need to know what are the causes of increased metabolic acidosis with an increased anion gap. So we'll end up here with diabetic ketoacidosis, okay? Just remember the mnemonic, the cat mud piles, okay? So here we end up with the D. So analyze the case below regarding acid-base diagnosis. Correlate them with the probable diagnosis and then mark the alternative that presents the correct correlation. Okay, so let's analyze each case. 50-year-old man, COPD. We need to remember that the COPD patients will have a higher value of the PCO2, okay? And that's completely normal for these patients because it's a chronic disease, okay? Okay, he has severe diarrhea. Okay, let's remember severe diarrhea will cause metabolic acidosis with an normal anion gap, guys. Okay, due to pseudomembranous colitis. Okay, so he has an infection. The laboratory evaluation reveals, okay, sodium 106. Okay, so in this question, we need to find out what's happening here in the first case, okay? So is it a metabolic acidosis? Okay, we actually, okay, it's a pH of 6.97. It's a very much lower number of pH, okay? There's even some indications for patients with this kind of pH to receive by external bicarb, okay? So, of course, okay, let's see the bicarb. Bicarb is 9, so it's a metabolic acidosis. So, is it a metabolic acidosis with an increased anion gap? Let's calculate the anion gap here real quickly. Okay, so it will be 136 minus chloride, it's 115, and bicarb 9. So this value here will be, okay, 124. So the anion gap here, it will be equal to 12. Okay, so it's normal. Okay, it's a normal anion gap. Because he has diarrhea, okay? If we were in a rush in a test, we could just think that it was normal, okay? So it will be is there also a respiratory acidosis? Okay, we will need also to calculate the expected PCO2 here in this situation. So let's do it. So it will be 1.5 times the bicarb. 1.5 times 9 will be equal to, let me just think here, it will be 13.5 plus 8. Okay, so we will end up with 21.5 for the expected value of PCO2. So we have a 40 PCO2. We also have a respiratory acidosis going on here, guys. So I think we will need to think about an increased anion gap in here because, like I told you, we need some reference says that this value needs to be lower than 12. Okay. So let's do the second one. So then after we can see the answers. Patient with septic shock. Okay, if a patient with septic shock, we can expect a lactic acidosis in here. Okay, just remember that it's also a cause of metabolic acidosis. Okay, so undergoes biochemical and gasometric evaluation. Okay, so he's acidotic in acidosis 7.22. Also a metabolic one with a lower bicarb number. Okay, so let's calculate the anion gap in here. It will be 1.125 minus 87 plus 8 and 95. So it will end up with a value of 30 in here. Okay, so we have increased anion gap in the second one. So let's see. Okay, so the second one, it will be a metabolic acidosis. Okay, let's also calculate the PCO2. It will be 1.5 times bicarb. It will be 12 plus 8. It will be 20. Okay, there's no respiratory acidosis going on here, guys. So the case 2, it will be the letter C here. It's a metabolic acidosis with an increased anion gap. So we can erase some these ones in here. So the first case, it will be metabolic acidosis with an increased anion gap plus respiratory alkalosis. No, it's a respiratory acidosis because he's retaining CO2. Okay. Okay. Oh, it's also it's not. It's one could be B or D. Okay, hyperchloremic metabolic acidosis plus respiratory alkalosis. Also no. So we will end up in here with a hyperchloremic metabolic acidosis with a respiratory acidosis. Okay, guys. Why hyperchloremic? Because we have a higher value of chloride in here, guys. Because of the severe diarrhea. So we end up with an increased value for chloride, guys. So that's all for the class of today. I hope you liked. Don't forget to subscribe to the channel. Leave a like on the video, okay? Thumbs up. And I see you soon in the next class. So bye bye.